Hello, welcome to Econometrics Melody. In this video, we will discuss about the hypergeometric distribution. Before that, let us see some of the useful functions. First of all, the factorial values. Let us learn to calculate the factorial values. In Stata, we'll calculate the factorial values by using this expression. Exponential and logarithm are inverse to each other. That is what they cancel out each other's effect, and we are left with the factorial value. The factorial of 0 is 1, factorial of 1 is 1, and so on. Factorial of 5 is 120, factorial of 6 is 720. And the factorial of 30 is this big number. Now let us say another useful function, combination, and this is how we can calculate the combination. So the explanation goes like this. There is one unique way in which we can select nothing out of 3 objects. There are 120 unique ways in which we can select 3 objects out of 10, and there are 167,960 unique ways in which we can select 9 objects out of 20 objects. And this combination is very useful to calculate the CDF and PMF of a hypergeometric distribution. Let us see some of the formula and we'll explain it as well. So the mean is calculated by n multiplied by k by n, where n is the number, let's say for our convenience, n is the population and k is the attribute of interest in that population, and n is the sample. So k by n, if we consider it is p, it is somewhat equivalent to the mean of the binomial distribution like np. And the variance of hypergeometric distribution is calculated by this formula, and we can also express it in terms of mean. N k by this n will be mean. So mean into n minus k into n minus n divided by n into n minus 1. Now the probability mass function is hypergeometric distribution is discrete distribution. Discrete probability distribution, we can calculate its probability mass function by this bunch of combinations notations over here, where k is the attributes of interest in the population n, and small k is the attribute of interest in a small sample n. In our sample n minus k, so exclusive of the attributes of interest in a population n minus k, and small n minus small k, so this is the exclusive of attributes of interest in our sample, and this n divided by n is the number of which we can take the n samples out of n population. The CDF is actually the summation of our PMF. If we want to ensure k or less attributes of interest in the sample n, then we add the individual PMF ranging from 0 to k, and this is going to be very simple. We'll demonstrate it in our example as well. N is the population and k is the traits or attributes of interest in the population, and small n is our sample, and we want to ensure k small k the number of traits or the attributes of interest in the sample n. And let us see it by the help of example. First of all, we are going to calculate the CDF of hypergeometric distribution. And hypergeometric, this is the Stata function. It requires the parameter n, capital N. Let us call it the population, capital K. So in the population, k number of attributes of special interest of our interest, and we are taking a sample of 10. This is a small n, and we want to ensure 5 or less objects in that sample of 10 having the attributes of our interest. And let us see what is the value of here, and it is nearly 17%, and this is the generic formula for that. So we want to ensure 5 or less objects of having special attributes, so we add the individual PMF from 0 to 5, 0, 1, 2, 3, 4, 5, and this should also result nearly 17%. Their values should be equal. Both of them should actually yield the same result, and let us compare them. So it is 17%, nearly 17%, and we want to see it by the help of CDF graph. So hypergeometric CDF, it is a user written program to demonstrate the CDF, which takes the parameter capital N and the attributes of interest k in the population n and sample 10, and let us see 5 or less, we should get 17%. So 5 or less, it is somewhere here, nearly 17%. And the ladder nature of this CDF graph, it indicates that the hypergeometric distribution is a discrete distribution. And let us see another example in which we are taking the population to be 50 for our convenience. We are calling it population. In a population of 50, there are 30 objects having attributes of interest, and we take a sample of 15 without replacement, and we want to ensure 9 objects having the attributes of interest. In a sample of 15 each, we want to ensure 9 or less objects having the attributes of our interest. In the using the generic formula, we add the individual PMF from 0 to 9, ranging from 0 to 9, and let us say both of them should yield the same value of the probability. And in both cases, it is nearly 62%. And from the user written CDF formula, let us see, check it. For 9 or less, for the 9 or less, it is 9 over here. 9 or less, it should be 62 or the percent. Yes, 62%. Similarly, we can provide any other inputs for the value of n, k, and small n, that is sample, and the attributes of interest. And we can generate the CDF of the hypergeometric distribution. This is what it looks like for the population of 300. Out of 300, there are 200 of them have some special attributes of interest, and the 90, in the sample of 90, we are going to get so many objects of the special interest. Now let us move to our PMF, probability mass function, and this hypergeometric P, this is the Stata function in order to calculate the PMF of the hypergeometric distribution. Here n, capital N, or the population, so 30, and k is 20. 20 of them have the attributes of certain interest, and we are taking a sample of 10, and we want to ensure 5 of them should have the certain attributes of interest. And let us see what is the probability like. It is 13%, and this is the generic or the real formula, a bunch of combinations together, and both of them should actually yield the same result. It is 13%, and a hypergeometric PDF. This is the user written program to generate the PMF of the hypergeometric distribution, and this is what we get. So 5, it was somewhere, the value is somewhere over here, 14%, or was it 14% or value 13%? Yes, right, it was 13%. And let us say another example. Here we are taking the population to be 50, and 30 of them have the attribute of interest. We are taking a sample of 15, and we want to ensure 9 of them should have the attributes of interest, and by the both of the formula we get the same value. It's 25% nearly, and let us check it. So 9, when it is 7.58, and then 9, it is this value, 24 or 25. Similarly, in this function, we can, in this program, we can provide any other inputs for n, capital K, and a small n, and we will get the PMF for so many small k's, or the attributes of interest in the sample. At the backdrop, we have a normal distribution with the mean and variance equal to the mean and variance of this hypergeometric distribution, and it seems that it is coinciding with the normal distribution. Now let us draw the distribution, and as we have seen in our formula, E by n, attributes of interest in the population divided by the number of population, it is going to act as a probability. And here 15 divided by 50, the probability is nearly 30%. So let us draw the PMF, and it should be somewhat right-tailed, because the probability is only 40%. When we compare it with the binomial distribution, if the probability of success is less than 50, then we will get a right-tailed graph. So at the backdrop again, we have a normal distribution with the mean and variance equal to the mean and variance of this hypergeometric distribution. And let us now create the probability to be 50%. So 30 divided by 60. So the probability, the value of P is 50%. And if we have the probability is 50%, we'll get a more symmetric graph. And let us draw it, and we will see that the graph will be symmetric. So in a population, when the 50% of the elements are of special attributes, having the special attributes of interest, then the graph is, its PMF is a bit symmetric. Now let us see another example where the probability k by n, it is more than 50%. In this case it is 70%. 35 divided by 50 is 70%. So in that case the graph will be left tail. Now let us simulate for the larger number of n, and here we have the capital N, or the population 300, and the sample, the attributes of interest to be 200. So 200 by 300, it is nearly 67%. And for this sample 25, we are going to draw the PMF, and it looks something like this. The red line representing the hypergeometric distribution nearly coincides with the blue line at the backdrop representing the normal distribution. This is what we want to demonstrate, and let us increase the sample small n to 35, and this time we see that the graph is more converging to the normal distribution. And this is, now let us increase the sample to be 45 and see the nature of the graph. As we increase the sample, we see that the graph is, the hypergeometric distribution is nearly converging to the normal distribution with the same mean and variance to that of the hypergeometric distribution. This time the sample is 95, and we see that it's nearly converging to the normal distribution. And let us increase the sample to 120, and yes, now let us again simulate the value of sample. So we are increasing the sample from 20 to 30, and for the population 100, and the attributes of special interest to be 60. And let us draw the graph, and we will see the graph, the single graph, and it's 21, 22, 23, 24. 60 by 100 is 60%. That is why the graph is not a bit symmetric. It has more of the left tail, but as we go on increasing the symmetricness of the graph, it increases, meaning thereby it takes the shape of the normal distribution. This time the probability is exactly 50%, and we're going to increase the sample from 15 to 25, and we will draw the graph in a same graph, and let us see what does it look like. So as the probability p is 50%, the graph is more of a symmetric one. If you look at this hypergeometric distribution, we see that the graph is more symmetric. And at the backdrop, we have a normal distribution with the mean and variance equal to the mean and variance of the hypergeometric distribution. Now let us see the area graph that is useful for the hypothesis testing, and let us see, this is again a user written program. We have written it. So our null hypothesis, the hypergeometric distribution, this hypergeometric distribution is drawn when we consider the null hypothesis to be true, k is equals to 8, and we want to test two alternative hypotheses, one tail test, and k is less than equal to 8. So let us test it. So for this graph hypergeometric distribution, for k is equals to 8, k is less than equal to 8 is covering only 1% of the area. So there is enough room to ignore the null hypothesis. We can, in other words, we can say that 1% area, this does not cover the property of this null distribution or this hypergeometric distribution. K is less than equal to 8, we reject the null. We prefer to say that k is less than equal to 8. But in another case, when k is equals to 8, for this alternative hypothesis, this condition covers most of the region of this null hypothesis, k is equals to 8. So we would rather go for k is equals to 8, and we fail to reject the null. Now let us say another example and try to explain. So this is the very basics of the hypothesis testing, and we have, this is again a user written program. We have written it, and we can provide the population n, capital N, population k, the attributes of interest, and this is the ESN sample, and the attributes of interest in the sample. And for this, let us again try to test the hypothesis, only one tail test. So we have drawn this hypergeometric distribution assuming that k is equals to 15. So the sample contains 15 elements, which carries the attributes of our interest, and we want to test the alternative hypothesis. Does it carry less than 15? So for less than 15, it covers most of the region of our null hypothesis, k is equals to, and the area is 98%. So we fail to reject the null in this case, and in another case also it covers 6% or 7% of the area, which is greater than our critical value 5%. So we fail to reject the null in both of the cases. Now let us see another example for the hypothesis testing, and in this case 150 by 300, again the p is 50%, and that is why we see the graph is more symmetric in comparison to the earlier one. And we have drawn this hypergeometric distribution assuming the null hypothesis k is equals to 6. So this graph represents the hypergeometric distribution, represents that the sample contains 6 attributes of our interest, and we want to test the hypothesis whether it contains less than 6 or greater than 6. So in both of the cases, as we say, they cover significant portion of the null region. That is why we fail to reject the null. And the last example, let us see, we have a different different values for the parameters, and we are going to test. So this is again a hypergeometric distribution, and we have drawn it for k equals to 13. This is our null hypothesis, and our alternative hypothesis, we want to say actually in a sample. So sample contains the attribute of interest, the elements there are 13 or less, and this covers only 2% of the area. Our critical alpha value is 5%. This is less than 5%, so we reject the null. So this minimum 2% area does not cover the enough properties of this distribution. And if the alternative hypothesis k is greater than or equal to 13, it covers 99% of the region, and that is why we fail to reject the null. Now let us see some of the usage of the hypergeometric distribution. Hypergeometric distribution is useful in case of sampling without replacement, and the while binomial distribution, it considers the draws with replacement. This is the difference between binomial and the hypergeometric distribution. Similarly, if we want to model the number of defective products in the consignment, we use the hypergeometric distribution, and this is what we mean by random sampling. For statistical quality control, we use hypergeometric distribution, and in a situation where we want to ensure certain properties should be included in a sample that is contained in the population, then we use the hypergeometric distribution. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.